This lesson is about wave characteristics. There are many different types of waves. We have water waves, sound waves, light waves. People make waves at a sporting event, and even zombies come in waves. But as far as we're concerned, a wave is a continual disturbance, oscillation, or vibration that transfers energy from one location to another. An oscillation is a regular variation in magnitude or position. So this is something moving up and down over and over again, or left and right over and over again, or something like that. This is very important to note. A wave transfers energy without transferring mass. If you have only a single oscillation, we call that a pulse. There are two main types of waves. The first is called mechanical waves. This is a wave that travels as an oscillation of a medium. Examples of mechanical waves are water and sound. Water waves are the oscillation of water molecules, and sound waves are the oscillation of air molecules. Mechanical waves cannot travel through a vacuum because they require something physical to be there oscillating in order for the energy to transfer. The other type of wave is electromagnetic waves. These consist of electric and magnetic fields, and an example of this is light. We'll come back to electromagnetic waves in a few lessons. Looking only at mechanical waves, there are two other categories of wave. The first is a transverse wave. This is a wave in which the particles of the medium oscillate perpendicular to the motion of the wave. Here's a simple diagram that you could copy into your notes that shows us basically what a transverse wave looks like.
In a transverse wave, the disturbance that makes up the wave is perpendicular to the direction in which the wave travels.
The other type of mechanical wave is a longitudinal wave. This is a wave in which the particles of the medium oscillate parallel to the motion of a wave. This diagram is a little bit more complicated. This is basically the coils of like a slinky, and you can see in some places the coils are bunched up really close, and in some places the coils of the slinky are spread out a little bit more. Try to copy something like that into your notes. It will be important for you to know that sound waves are longitudinal.
In a longitudinal wave, the disturbance that makes up the wave is along the direction in which the wave travels. Longitudinal waves are also referred to as compression waves.
The focus of this lesson is to learn about the different characteristics of waves. We'll mostly be looking at transverse waves, but these characteristics apply to both transverse and longitudinal. Here's a quick list of the characteristics we'll be looking at. Wavelength, which is abbreviated by the Greek letter lambda, kind of looks like an upside down lowercase y. Amplitude, frequency, period, which is a capital T, as opposed to the lowercase t that we use for time, and speed. Now we'll take a look at each one of those individually. Before we go any further, let's introduce a couple of terms that will help us describe the different parts of a transverse wave. The peaks of a transverse wave we'll call crests, like the crest of a hill. The valleys of a transverse wave we'll call troughs, kind of like the thing a pig eats out of, a trough. So with that terminology in mind, we can say that the wavelength of a wave is the distance between consecutive corresponding points. Wavelength, being a length, is measured in meters. So corresponding points are 2 points that match. They're identical points on neighboring oscillations in the wave. Right? That's what consecutive means, one right after another, so neighboring. There are literally an infinite number of places we could label or measure the wavelength. There are a few that kind of make the most sense. So here's one example. This is from the beginning of a crest on one oscillation to the beginning of the next crest. Another logical place to label or measure the wavelength is from the top of one crest to the top of the next crest. Those points are obviously corresponding to each other, they match, right? And there's no other crest in between. Likewise, we can measure from one trough to another trough, and really we can measure between any points that meet those criteria. So here's just a random one. So 3/4 of a way through a trough to the next point that is 3/4 of a way through a trough. Amplitude is basically the height of a wave, but we have to measure it very specifically. It's the distance from the middle of the wave, that dotted line, to the top of a crest or to the bottom of a trough. This means that we can measure the amplitude here, or we can measure the amplitude here. Really, the only other thing that you'll need to know about amplitude is that the energy of a mechanical wave is directly proportional to its amplitude. Okay, how about frequency? A really broad way we could define frequency is the number of occurrences of a repeating event per unit time. But don't write that. For us, we'll describe frequency as the number of complete wavelengths produced per second, or the number of oscillations per second. There's no equation for this on the reference table, but we could sort of write it in the form of an equation like this. F for frequency is equal to the number of wavelengths that you see in a picture or that are described to you. That's number of complete wavelengths, or number of oscillations, or number of crest-trough pairs, however you want to think about it, divided by time. We have a new unit that goes along with frequency. It's called a hertz. Now the abbreviation is capital H lowercase z, and H isn't a prefix. HZ is the abbreviation for hertz. And it basically means cycles per second. Let's take a look at an example of a problem involving frequency. So here's Frank, and he's making waves on a rope by moving his arm up and down, which he does 20 times in 10 seconds. So in 10 seconds, he moves his arms up and down, that's an oscillation, 20 times. So we want to figure out what are the frequency of the waves that he's making. So frequency is the number of wavelengths that are created divided by time, and we can see from the description that he's creating 20 wavelengths, that's 20 oscillations, every 10 seconds. So we have 20 divided by 10 seconds. Notice the 20 doesn't have any units. We don't measure that, it's just we counted. We counted to 20. 20 divided by 10 seconds gives us a frequency of 2 oscillations per second, is a way we could describe that. And if we want to put our new unit on there, which we do, we can call that 2 hertz. Let's take a look at period. Again, the very general definition we can write for period is that it's the interval of time between successive occurrences of a cyclic phenomenon. But again, don't write that. For us, period is the time for one complete wavelength to be produced. In other words, this is the time for one complete oscillation. Just like we did for frequency, we're going to write this in sort of an equation form. Like what we wrote for frequency, this is not in the reference table, but this is a really convenient way to think about period. So you take all the time that has passed while the waves were created and divide it by the number of wavelengths that were produced, or again, the number of oscillations. The unit for period is just second. Let's take a look at an example. So Kelly is floating on an inner tube in the ocean, and she notices that she bobs up and down 6 times every minute. So each time she bobs up and down, that's one complete oscillation, that's one wavelength. So we can figure out the period of the ocean waves that she's floating on if we do a little bit of math. So period is the total time that has passed divided by the number of wavelengths or oscillations produced within that time. So the time that she measured was 1 minute, so 60 seconds, divided by the 6 complete oscillations that she observed gives us a period of 10 seconds. So she bobbed up and down in 10 seconds, and then bobbed up and down again in another 10 seconds, and so on and so forth. Frequency and period have a unique and important relationship. Take a look at the equations you just wrote for them. Do you notice that the equation for period is just the equation for frequency flipped upside down? Or I guess you can say it the other way around. This is because frequency and period are reciprocals of each other. This means that we could write a very simple equation that relates frequency and period. We can write it either as F equals 1 over T or as T equals 1 over F. And finally, let's talk about the speed of waves. The speed of a wave means exactly the same thing as the speed of a car, or the speed of a person, or the speed of anything. It represents how quickly a wave can get from one place to another. what we're going to do here is figure out an equation for the speed of a wave based not on how far it travels and how much time that takes, but the fundamental properties of the wave itself. Watch. Okay, so let's start with something we already know. V equals d over t. Speed equals distance over time. Now let's think about the new stuff that we learned. Right? The characteristic of a wave that's measured in meters, like distance, is wavelength. And the characteristic of a wave that's measured in seconds, like time, is period. So let's rewrite that equation that we've known since September as V equals lambda over t. That is, the speed of a wave equals the wavelength of the wave divided by the period of the wave. Now remember, we just learned that period and frequency are reciprocals. This means that we could also write the equation for the speed of a wave as V equals f lambda. And that's actually the way that it's presented on your reference table. Let's take a look at a couple examples using the new wave speed equation. So we want to know what's the speed of a water wave that has a wavelength of 8 meters and a period of 4 seconds. Well, it's pretty straightforward. V equals lambda over t. Now we wrote this equation because we know the period of the wave, not the frequency. We can plug in our 8 meters and our 4 seconds, and we can find out that the speed of this wave is 2 meters per second. Notice, we didn't have to know how far the wave ultimately travels or how long it takes to get to its destination. All we had to know were those two fundamental characteristics of the wave itself, its wavelength and its period. All right, let's take a look at another example. What is the wavelength of a sound wave with a speed of 331 meters per second and a frequency of 500 hertz? Now this time, since we know the frequency, we'll write the wave speed equation that has frequency in it, V equals f lambda. And we can plug in our speed and our frequency, and when we divide both sides by 500, we can find out that the wavelength of this wave is 0.662 meters.